No, the screen's still washed out.
All right. Sam, can you see my screen?
Yep.
All right, perfect. Okay, everyone, we'll get started here. My presentation today is on superconducting chip design and simulation. So before I get into that, I kind of want to just give some background about myself. So this is my timeline of sort of my quantum journey, I guess, becoming a quantum engineer, so to speak. So in 2022, I graduated from San Jose State with a bachelor's in physics. I had a quantum foundations focus. That was sort of the research I was working on heavily at the time. During that time, I would have considered myself a physicist because I had the degree. So I earned my stripes with that. I claim myself to be a physicist. I was an experienced, I would have considered myself an experienced programmer. I was very versatile with Python and all that stuff, but not so much experience in engineering or lab experience. I did not have that. Later on, the summer following that, I did an internship at Air Force Research Lab in Rome, New York. And there I did a quantum algorithms internship. And I knew absolutely nothing about quantum computing prior to this internship. I literally learned the basics, what an X-gate was, what a Hadamard was at this internship. So that was the beginning. That's what sparked it all. And then after that, I began the Masters of Science Quantum Technology program at San Jose State. And a semester after that, I began my quantum engineering fellowship traineeship. And during that time, I began doing superconducting chip design in collaboration with San Jose State and Lawrence Livermore National Lab. And so at the bottom here, I sort of have this timeline of me starting out with my bachelor's physics degree and working my way to this intersection of quantum information science and engineering. Okay, so what is my research interest is quantum entanglement. And I remember when I first learned about this thing, I was very baffled by it, which I feel like most people are when they first learn about quantum entanglement. And I asked myself 3 natural questions. What is it? How do you do it? And why is it useful? Why do we care about these things? And I was so overly interested in each of these questions that till this day, I'm still asking myself the set of 3 questions that I asked myself at the very beginning and focusing into each of these questions in so much in depth that each of these spiraled into their own research projects. So what is it turned into more quantum foundations research with Dr. Ken Warden, discussing what's really happening when you entangle 2 particles. And he's giving a guest seminar for that on October 28th. So if that sounds interesting, I recommend that you attend that seminar. And how do you do it? Well, you do it through superconducting chips, and that's research I'm currently doing with Dr. Wong on the electrical engineering department in San Jose State. And we're asking the question, how can we utilize microwave signals to do single and 2-qubit gates? And why is it useful? Well, you can use it to solve a very difficult class of math problems called combinatorial optimization problems with quantum computers. So if you have entanglement, that's kind of your key special feature to build a quantum computer. If you can build a quantum computer, you can do a bunch of complicated math problems that are very difficult for normal computers to solve. And the focus of today's talk is going to be superconducting qubit chip design research. So how do you do it? How do you make entanglement? What is the machine doing? How do you build it? And the big picture goal here, so this is sort of the timeline of the project. So at the very beginning, you have to do chip layout, right? You have to design a chip using some sort of CAD software. In my case, I use Qiskit Metal. And then you have to simulate it. So you have to see how signals behave in the chip. So here I used I'm using HFSS, which is high frequency structured simulator. And then you want to optimize the design for exceptional qubit coherence. So you're feeding the qubit information with these signals, and you want the qubit to actually hold on to that information. And so you want to optimize these T1 and T2 times. And lastly, you want to understand how to map these electrical signals to single and two qubit gates. So for example, what I'm really after in the long term is the I-swap gate. The I-swap gate is the entanglement gate for superconducting qubits. And if I get the I-swap gate, then I have a computer that's fundamentally different than the rest. It has an inherent quantum ability that regular computers just cannot do. And right now I am here. So on this timeline of progress, I'm sort of in between step 1 and step 2, still designing the chip and tweaking and making adjustments and doing simulations. So communicating with qubits. So you can't just poke your qubit with a stick and say, hey, come on, do an X gate. You have to communicate with the qubit on their level. And the language of qubits are photons. Qubits love photonic interactions. So all a qubit is, it's just an atom with its energy states truncated between the 0 and 1 state. And if you send a photon at an atom whose energy matches the energy difference between two of their energy states, the atom's going to say, hey, I like this. I want to utilize this photon, and I want to do some sort of absorption process, or I want to do some sort of stimulated emission. So if you send it a photon that matches the difference between their energy bands, they're going to want to interact with it. And what better way to interact with a qubit than with microwave electronics? So microwave electronics send E&M signals, electromagnetic signals, through the 300 megahertz to 30 gigahertz range. And this is sort of the microwave electronics schematic with your AC voltage source leading all the way down to your qubit. So this diagram is your qubit that says on chip. And E&M signals, well, that's just a fancy way of saying light, saying photons, right? So we know that a photon is just electromagnetic radiation. So usually we kind of think, okay, we're sending currents down this wire, but you can really think of sending a photon. So you're sending photons through this wire to interact with your qubit. And once you do that, your qubit can take these photonic interactions and you can have it jump up and down energy levels, right? Which is what you want it to do. You want your qubit to move between the 0 and 1 states. Okay, so this is what communicating with qubits looks like, from quantum algorithms to readout. So we start with programming some sort of code. In this case, it's Qiskit. And this is your quantum program for doing an X gate. And you can take that, feed it into some quantum hardware of your choice, and it takes these instructions and it does rotations on the block sphere. So in this case, it's an X gate, so it's going from 0 to 1. And the question is, how can we design hardware for successful qubit control? And an alternative way of asking that question is, how can we give hardware, how can we design hardware such that it follows our instructions? If we give it instructions that says, hey, do an X gate, we want our hardware to actually do that X gate. We don't want it to do something else. And the issue with this is, as you guys may know, that current quantum hardware is very oversaturated with noise. Current quantum devices are in their NISQ era, their noisy intermediate quantum scale. And we have lots of issues with noise. So how do you mitigate noise? Well, you can mitigate noise by doing a better design. Well, how do you implement a better design? Well, that's kind of a non-trivial question. There's really no clear answer, and that's why this is such an active field with research, and that's why there's so many different quantum platforms, and why there's so many different ways to design each platform. At least in the superconducting world, there's a lot of ways you can design a chip. And so which design is going to give you the best best coherence times and the best gate fidelities, it's still a very, very active field of research. Okay, so how do you do it? Well, you can do an exploratory investigation into chip design. Here's a current quantum chip here that I'm still working on developing. This, again, we used Qiskit metal to develop this. And Qiskit metal is accessible via Python. It's just a package. And it comes with wires, launch pads, transmon qubits, and other circuit elements. And if the package doesn't have a circuit element, you can custom create it, which you have to kind of open up the code and make your own elements. It's very tedious to do, but I had to do it. And I'll kind of go through each of these parts. So the chip here sort of has a whole anatomy to it. So kind of like the human body, you have a bunch of organs that work together to keep you alive. There's a bunch of parts here that are all working together trying to keep the coherence times alive of your qubit. At least that's the goal. So I'll kind of go through each of these electrical components and describe what how they're interacting with the electrical signals here. So first we have the launch pads. The launch pads are used for wire bonding into quantum machines. So where do you put your external wire? You plug it in right into there, and you wire bond it, and that's where you shoot your microwave signals for. And that's also how you retrieve them too. Here we have Josephson junction testing sites. So here you can just put a Josephson junction in and run some signals through it and test it and make sure that it behaves like it should. And all a Josephson junction is, it's just, you can think of it as a nonlinear inductor. So does it behave like a nonlinear inductor? That's where you test it. And then next you have the DC bias current line. And the DC bias current line is used for depositing magnetic flux into flux tunable qubits. So this line here, this bias line, is the only DC part of our circuit. The rest of it is microwave AC. And you might be asking, what's a flux tunable qubit? Well, it's this thing. And it has two Josephson junctions. So usually the transmon comes with one. This one comes with two. And the nice thing about the flux tunable qubit is that you can adjust its Josephson energy. And so what that means is that, let's say you don't like the amount of energy that's stored in the junction, you can actually tune that, and you can tune the parameters in your Hamiltonian to have your qubit act differently. And yeah, oh yeah, so this is the Josephson junctions, and this is a capacitor up here. Next, you have your two-qubit coupler, which is it's basically a capacitively coupled wire that couples two qubits together. And this is kind of the key ingredient to creating an ice swap gate. And then you have the resonator. The resonator only responds to signals hit at its resonant frequency, and it tends to kind of ignore the rest of the signals. And it's a coupling, it's an inductive coupling between the transmission line and a capacitive coupling with the qubit. And we have the transmission line, which is a coplanar waveguide. This is kind of how we send signals throughout our chip. So this is kind of like, you can think of the coplanar waveguide as your main freeway, right? So your freeway is kind of like your main road, right? That's your main street. And then your signals can kind of diverge through all these other routes here. And then you have, last but not least, the transmon, which just has one Josephson junction. And unlike its flux tunable counterpart, it's not tunable. So once you put the transmon into the chip, it is what it is. You can't change it. It's stuck with the parameters you gave it. So I know that was a lot. So I kind of took the time to divide the chip into three sections. So the top part of the chip is mostly component testing. It's testing to make sure that your components are working the way they should in the lab. The middle part is for entanglement. That's our two-qubit coupling. In the bottom part of the chip, that's the part that I'm working on right now. I'm just trying to work with independent qubits. So these qubits are non-coupled. And I'm trying to work on single interactions with each qubit. So I'm just sweeping the rest of it under the rug. Here's my rug. I'm out of sight, out of mind, only focusing on this part here, the bottom part. Okay, so this is kind of where the microwave theory comes in. So sorry if this part gets technical, but it's important. You can't do quantum engineering without a little bit of engineering, so you need a little bit of both. So transmission line, this is sort of the fundamental to any microwave textbook you look up. One of the first sections is always transmission line theory. So it's essential to talk about. And it's also essential to talk about impedance matching, which can cause absorption or reflections with microwave signals. So a matched impedance means signal absorption, and a mismatch impedance corresponds to reflections. Yes.
That pad on the bottom right, that's just left loading, or is supposed to be connected to the
This is something, this isn't connected to anything right now. So this is just connected to the ground plane. And the reason why that's there is because on the actual chip, there's these launch pads that are around there. So this isn't something that's designed, that's just something that's just an object that's there, and we have to kind of either work with it or work around it. So with impedance matching, why is this important? Well, we want to know if our signals are absorbed into our qubit or if they're reflected. This is sort of what it looks like. So we could have a transmission line with a characteristic impedance. And if the impedance matches the impedance of the load, we get an absorption. And yeah, that's a matched load. We have no reflections, and the entire signal is transferred. In the opposite case, we could have a mismatch where the load impedance could be a lot higher or a lot lower than the characteristic impedance, and we get a reflection. So this means that the signal wasn't absorbed by the load. It was just reflected off of it. Okay. We can add a little bit more complexity to our model by introducing resonators. So what are resonators? A resonator is just a coplanar waveguide wire that's inductively coupled with our transmission line. And they're usually squiggly. Only reason why they're squiggly is just to save surface area, because these wires can be long, so you kind of have to meander around to save space. And a resonator sort of behaves like a harmonic oscillator. So a harmonic oscillator will respond to its resonant frequency, and a resonator will also respond to its resonant frequency. So if you have two different resonators of two different resonant frequencies, this is a good way for controlling each qubit, because if I strike a F4 frequency through the transmission line, resonator 4 is going to care about that a lot, but resonator 3 is going to care about that so much, and vice versa. And from this, we can kind of see different modes to form. So you can sort of draw, in this case, just two, instead of two resonators, just one resonator, one transmission line. And here we start with a 7 gigahertz resonator and a 12.8 gigahertz driving signal. And we see a mode form in the transmission line, but nothing really in the resonator. But when we have our drive frequency equal the resonant frequency, you sort of get this activity in the resonator. So resonators are very powerful for qubit control here. And we can see that more thoroughly through some eigenmode simulations. So there's an analytical formula for calculating what the resonant frequency is for each of these meanders, and just by this formula here. So F4 has 7 gigahertz, F3 has resonator 4 has 7 gigahertz, resonator 3 has 6.8 gigahertz. And we can run eigenmode simulations to see different modes. So my simulation tells me, okay, I have my first 4 modes are at these frequencies, and I can look more thoroughly to see how the energy is stored in each mode. So the first mode is at 6.73 gigahertz at 1 joule. I just put in 1 joule of energy to see what the system would do with it. And I see that the energy is sort of stored in the rightmost resonator here. Second mode, I have the energy stored in the leftmost resonator. In the third mode, I get a coplanar waveguide or transmission line mode here, where I have the energy stored here, and it sort of looks like the first fundamental mode, where you have a node, antinode, and node. So it's kind of like a standing wave or something, which is expected. We can go into the fourth mode, which is a weird mode. I don't really know what it's doing here. It seems like it's laterally storing energy in the transmission line. I'm not really sure what this means, or if this is accurate, but it just goes to show that there's no substitute for simulation. You really don't know how a system is going to behave until you simulate it. You can do as much pen and paper math as you want, but there's no substitute for this. You got to do simulation to know how your system is going to behave. Okay, now the quantum part, which is adding in qubits, right? You can't do quantum without qubits. That's the secret sauce. That's a special ingredient that you need. So we can add in 2 qubits, and we get a new set of eigenmodes. So those are experimental results. And again, I want to ask myself the same question: where is the energy being stored here in each of these modes? So first mode is a qubit mode. It's a transmon mode. I see that most of the energy is stored in the transmon and in the Josephson junction here. The Josephson junction is just represented by that tiny rectangle underneath this tab here. That's not actually what a Josephson junction looks like. It's just a placeholder for one. You can go in the second mode, which is also a transmon mode. This one's in the flux tunable qubit, which, if you recall, the flux tunable qubit has 2 Josephson junctions. So this is where the second mode is at. And mode 3 is a resonator mode. On the right-hand side, you have a little bit of electromagnetic activity here. And the fourth mode is also a resonator mode on the left-hand side this time, with some electromagnetic activity there. Mode 5, we get the standing wave behavior that we saw before, which is expected. This is a good sign that we're seeing consistency of before and after we added in our transmon qubits. So there's something else fundamental about the system going on. And mode 6 is also, it seems to be a copy of mode 5. Again, I don't think this is accurate. I think this is just a weird simulation thing going on, especially because these frequencies are so close together. But I didn't want to throw out any results, even if they were bad. Yes.
I understand the significance of these modes, but I think ultimately you just want to drive a signal that couples into that resonator that drives those connections. So that would be basically, and I presume a certain frequency, right? That would be your second. So I use these modes, one of those frequencies would end up in these modes. Is that what you're trying to say?
Yes. So these are the key frequencies that we're trying to find all the different ways that our system can store energy. And so there's certain key frequencies that map to certain parts of the circuit. So for example, if mode 2, right? If I'm interested in interacting with this part, I'm like, oh, this part of the circuit really likes 5.41 gigahertz.
The coupler needs to be able to couple to that frequency as well. So if the signal is coming from that launch pad, and let's say, because the signal is coming from the launch pad, right? So it has to get to the transform, and to go to get to the transform, first you need to go to that coupler.
Right.
If the coupler is not designed to couple at that frequency, then how would you interact with that transfer? That's all I'm trying to say. Like, it's like a whole network thing.
Yeah.
You look at it as a whole network. So, yes, I understand there are modes and how each circuit responds to these different mode frequencies look? Like, do you have like an ST1 chart in this simulation showing or
I do have an S201 chart. I don't have one in this presentation,
okay, so
but
where was that notch at? Was it in one of those frequencies or was it a different?
yes, it's gonna be in one of these frequencies. Yeah. So whenever there's a transmission, you're gonna see a spike in S21. Yeah, I'm trying to think of another way to answer your question. Yeah, let me get back to you on that.
The modes are tell you what's part of the circuit is getting excited at frequency. So they're essentially just taking that old substrate design and just exciting it to frequencies and see where
Exactly.
start to store energy.
Yeah.
So it's good mapping of what's happening in different part of the circuit. But when you're trying to drive the signal, now you're driving a chain, from your launch pad to the CBW to the coupler and then to the resonator. Now that's like a whole big network.
Right.
File.
Exactly. And so you can't really, once you do have a complicated system like that, you can't really talk about individual parts. You have to, that's why it's important to simulate it as a whole, because the eigenmode frequencies could shift if you add something new. So some different behavior could happen.
Is that what this simulation is doing? You're putting a voltage at one of the pads, right? And sweeping a bunch of frequencies or something is what, then this is showing us when you hit 5.41 gigahertz, the energy, when you hit 5.41s at the pad, that energy is being stored in sweeping.
Exactly. Yeah. So that's exactly right. So what I'm doing is I'm feeding through microwave voltage sources through one of the launch pads and at different frequencies. So I'm sweeping through all these frequencies, and then there's these special frequencies that happen at these certain modes. So for example, at 5.41, I see a bunch of electromagnetic activity in one area, but not really so much in the rest. And you can kind of see the chart that the magnitudes vary.
Okay, so that
Very
would
low.
Okay, so you want to go, then means there's something at 5.40.
Yes.
So otherwise there wouldn't be any energy at that part of the circuit.
Right. So this bottom part, this isn't zero. There's still blue isn't zero. There's still some energy going on here. Yeah. So don't worry about that. Yeah, so that's what I'm doing. I'm sweeping through different frequencies, and I'm hand picking out the ones that correspond to, okay, this specific part of the circuit is super bright, which means that this part, I can manipulate this part of the circuit with that frequency. Okay. So next is, what you might have noticed is I haven't done any quantum-based simulations yet. This is all classical E&M simulations. And so we have to kind of we have to find a way to describe our system within some sort of quantum framework. And the way you do that is through EPR simulations. Well, that's at least one of the ways you can do it. And EPR stands for energy participation ratio. It's a number between 0 and 1. And it tells you how much energy is stored in the Josephson junction. So an EPR of 0 means that there's no energy stored in the Josephson junction. And EPR of 1 means that all the energy is stored in the Josephson junction. And EPR gives you some insight of how dissipative the junction is. So it tells you something about the performance of your junction and the performance of your qubit overall. And you can also find this in the EPR Python package. So when I kind of look through all these hand-picked modes where I see one part of the circuit light up, I kind of have my qualitative observation where kind of for mode 1, I said, oh, the transmon mode. I mean, the transmon part of the circuit was really bright. So that's a mode for there. I get a very good EPR. I get an EPR of 0.987. And this is really good because qubits should have a lot of Josephson junction activity, right? That's what makes that's one of the key ingredients that makes a qubit is the Josephson junction. For the second node, however, for the flux tunable qubit, I get a very low EPR, and this is really bad. This is very, very low Josephson junction activity. And I think the only reason I'm getting this is because I didn't define the junction very well in the EPR simulation. So that's something I still need to fix. So I want to show you guys the good and bad of my results. So for mode 1, I don't need to troubleshoot, but mode 2, I need to troubleshoot in PyEPR and still try to figure that out. And for the rest of these modes here, the EPR is low for what, and that's what we expect, right? For resonators and the transmission line, these are classical circuit elements, and so we don't expect them to display any type of quantum behavior. That's why they have EPR values that are 10 to the minus something, very small number. So that's one. And you can also use EPR to calculate quantum effects. So anharmonicity and cross-curve. So I get back this matrix here, this chi matrix, and we find that the diagonals of this matrix are the anharmonicities of each element, and all that anharmonicity is, it's well, a way to put it in short, it's an ability for a qubit to stay within the 0 and 1 state. So if you have a higher anharmonicity, a qubit is more likely to get stuck between the 0 and 1 states, and it won't go off and wander the other higher energy states like 2, 3, 4, all those things. And the off-diagonal elements are the cross-curve, and cross-curve is a way that we can analyze nonlinear effects between different circuit components. And we can also calculate something very important called the dispersive shift. So dispersive shift is very relevant to readout. So I haven't actually done this calculation yet, but this is sort of one of the big milestones that I hope to achieve soon, is using our chi matrix to calculate the dispersive shift. And all dispersive shift means is how well can you distinguish your 0 state from your 1 state. So if you have a low dispersive shift, you can kind of think of these 0 and 1 clusters very close together, and it's very difficult to read what your outcome was. Was it a 0 or a 1? Well, you don't really know because these clusters are kind of overlapping. But if you have a higher dispersive shift, then these clusters are more separated and it's more easy readability. So my dispersive shift for my flux tube my dispersive shift for my transmon is most likely good, but I still need to do some more troubleshooting to figure out what my dispersive shift might look like for my flux tunable qubit. Yes.
Your dispersive shift, it's a dispersion between what two things? Is it the 0 state and the 1 state? Like
Yeah, so you can think of the dispersive shift as this shift right here, this gap, and you can think of this purple, this dip here as your 1 state. So anything that falls into this category is your 1, and anything that falls into this category is your 0. You can kind of see that if you take the shift and you bring it to 0, you kind of have these wells overlapping. And it's very difficult to tell what's your 0, what's your 1. So it's very important to have some sort of shift to keep your 0 category and your 1 category separate.
But I guess I'm confused. Isn't the 0 and the 1 states energy gap defined by how you were designing the circuit in the first place? Like, isn't this just energy gap between the 0 and the 1 state, or am I missing?
That's a good question. I'm not really sure how to answer that, because to be honest with you, I haven't gotten to the readout part of my project. This is kind of the bigger overarching plan that I have in my mind to get to the dispersive shift, but I haven't actually gone through the calculations or how to get it yet.
I think that cluster relates the energy difference to the difference. And that's the engines. So yeah, you're right, there's energy stuff for those two eigenstates, but for measuring that energy, we need a way of doing it with electronics. And one way to do that with electronics is to firing a RF signal and measuring the reflection, and discharge with illustrate how you do that. Now, because your two states have the same frequencies, essentially when you fire a signal that's in the middle, by reading the IQ phase, you can determine whether it's between one states.
Yeah, I guess science, quantum mechanics, they would have, unless it was a, they would have two different frequencies together, but yeah, I don't want to live with what we like.
Yeah, but that's a very, that's a very, very important point. Also, yeah, that to actually extract these signals that you want reflections of your microwave signals too. So you want your microwave signal to reflect off the qubit, so that way it carries information about the qubit to read out. But I haven't gotten into that part yet super thoroughly. But yeah, that's kind of the future goal.
Your readout frequency is, let's say, 6.07 gigahertz. What's your excitation frequency?
From this? Oh, this is just a plot that I adapted from another source.
Yeah.
So that this isn't mine. I'm just kind of borrowing it to show what behavior I want to replicate. But I have references at the end, and you can take a look more at the paper. Okay. So the conclusion here, how to design a quantum chip in a snapshot, is you kind of go through this engineering life cycle here, where you go from design to classical simulation to quantum simulation and interpretation. Then you go back and you repeat the cycle, adjust your design, redo the simulations, and do this over and over and over again until you get parameters that you're satisfied with. And once you get parameters that you're satisfied with, that can do, then you can move on to doing single and 2-qubit gates, which is what we want at the end. And yeah, this is kind of the caveats of these different processes. So layout is difficult because there's many design choices that you can make. E&M simulation, it kind of tells you how you communicate with your hardware via microwave pulses, and there's no substitution for this. You have to do this. You can't just do pen and paper work. You have to do simulation to really understand what your hardware is doing at a fundamental level. And you have to do EPR, energy participation ratio, which leverages the HFSS simulations to tell you the quantum features of your system. And down here is just a QR code to my portfolio, similar projects that I'm working on here. If you have any questions after the talk, please email me at james.saslow@SJSU, or feel free to put your questions in the Zoom chat. And I also want to remind you to be courageous in your learning. When I first started this project, I was very nervous to engage in something so much in the engineering world, in the electrical engineering world, being a trained physicist. But yeah, I was able to take things little by little, learn little by little, and I feel more confident with it. So if you're courageous, so yeah, I guess my closing statement is be courageous. If you're nervous about learning something, don't be so nervous. Try to take a stab at it, and it might turn out that it's not so bad. So yeah, I'm open to any questions that you may have.
So I have a few questions.
Sure.
So this cascade metal tool, you can, as I understand, you can script pretty much the circuit, and it will then generate the layout for you. Is that how you use the tool?
Yes, so you use Python to kind of describe where you want to put each circuit element and where you want to put it and which elements you want to connect together.
It's very high level, so it's almost like an algorithmic, well, it's almost scripted design. You can just write in high